All right, we're back. We're on page 3 of Notes 14 of Calc AB. We're talking about approximating definite integrals using different methods. So sometimes use rectangles. When you're using rectangles, you might use the left endpoint of an interval, the right endpoint of the interval, or the midpoint of the interval. So those are rectangles. Those are all called Riemann sums. Or you might just use trapezoid. And trapezoid is kind of, we saw the trapezoidal sum is actually the average of the left and the right Riemann sums. The midpoint sum is the most annoying. It has almost nothing to do with anything, and you'll find yourself using it, but like just not that often. So let's take a look at this problem and see what we can do. We got a car moving along a straight road. Its speed is continually increasing. All right, so that's important because an increasing function could look like this, or it could look like this, or I mean it could vary, but it's got to always be increasing. So now what we want to do, speedometer recordings, readings are recorded at 2-second intervals. So it's actually really common to be able to measure something's speed or velocity. I mean, think about a car, right? They have a speedometer. It's easy to measure speeds and velocities, so you often have these kinds of tables. It's actually a little harder maybe to measure like position over time without like a lot of really advanced sensors. But like velocity is pretty easy. I mean, we all carry a phone. Well, not all of us. A lot of us carry a phone that's constantly measuring these sorts of things. So you take these measurements, put them in a table, and you can make all kinds of inferences from them. And that's what we're going to be doing. So in the first 2-second interval, what is the minimum distance the car could have traveled? What is the maximum distance and why? So think about what we said. So we know that this is an increasing. So the velocity is always increasing. So the velocity might look like, so like, for example, here's, having a bad day with these lines, with all the like snap to type shapes. There's 2, so it's 30 and then 36. So like it could be the case that the function looks like this. It could be the case that it looks like this. It could be the case that it looks like this, right? In all cases, that would be increasing. There's 3 different possibilities there. But for all of them, if I make a left Riemann sum, so the interval is from 0 to 2, and then I'm going to do a left Riemann sum, right? So what I do is the left endpoint, I go up, I go over, I go down. So this is my left Riemann sum. That is clearly an underestimate, right? So why is it an underestimate? It's under because the function is increasing, this is guaranteed, at the left endpoint, is guaranteed to be the smallest value the function will ever have if the function is increasing. So if I basically say the function is always that value and use that to create my estimate, it must be an underestimate. So if a function is increasing, then a left Riemann sum is guaranteed going to give you an underestimate. So my underestimate, my estimate of the minimum distance. So the minimum possible, let's say the minimum possible distance is 2 times 30. So 2 is the base and then 30 is the height. So 2 times 30, so 60 feet. And then the maximum distance, by like a really similar argument, the maximum distance that we could ever have would be an increasing function. The biggest it'll ever be is at the right endpoint. So if we assume that it's that value the entire way through, it's got to be an overestimate. Like using the maximum value all the way through has to give you an overestimate. So the maximum possible, I don't know what happened to my handwriting in between videos, but it's gone, is 2 times 36 is 72 feet. Okay, so now we want to give a reason for this. So I'm going to say, whoops, since, what do we have, velocity? Yeah, v of t. Since v of t is increasing, a left sum, which you can abbreviate that way, that's pretty much fine, will underestimate, and a right sum will overestimate. And like, I don't think that exactly justifies it. I mean, like using the right endpoint, a better reason, I guess, which I just don't want to write, is that on the interval from 0 to 2, v of t is less than or equal to 36 for all t. So the maximum possible area we could get is 2 times 3672. On the interval from 0 to 2, the minimum possible v of t, or v of t, is greater than or equal to 30 for all t. So then the minimum would be 30 times 2. You know, those are better answers. But sometimes when you're taking your first shot at a problem, you don't give the best answer, and then you kind of revise it. I'm not going to write down my revision, but still. Find a lower and upper estimate of the distance the car could travel in the 8-second interval. Show your work. Okay, so I'm going to do, basically I'm going to do a left sum and a right sum. And I'm going to kind of do it, where am I going to write this? Okay, so I'm going to use this idea, right? So the function's increasing all the way through. So left Riemann sum will always give you an underestimate. So my lower estimate is going to be a left sum. So that's going to be the integral from 0 to, what are we doing, 0 to 8? The integral from 0 to 8 of v of t dt is approximately, or actually, let's say it's greater than or equal to, because it definitely is. Greater than or equal to. So what are we doing? A left sum. So here, let's get into how I really do these. So if I have a table, if I'm doing a left sum, what I'll do is this. I'm going to do 2 and then times 30. And then I'm going to do 2 times 36, 2 times 38, and then 2 times 40. So I'm going to do 2 times the quantity 30. I'll write it here and then just move it down actually. 2 times 30 plus 36 plus 38 plus 40. So this is my left Riemann sum. I'm going to move it down so that it's where the work should be. And then should we work that out? You know, I'll use a calculator in a minute. And then the upper estimate. So upper estimate is going to be the right Riemann sum because the function's increasing, which means on each subinterval, the biggest the function will ever be is at the right endpoint. So if I'm using a right sum, I'm getting the biggest possible estimate that I could get. So I'm going to say that the integral from 0 to 8 of v of t dt is definitely less than or equal to, and then let's go to the table again. So I mark up my tables quite a bit while I'm doing these. So this is going to be 2 and then 36, then 2 and 38, 2 and 40, and then 2 and 44. So it'll be 2, 36 plus 38 plus 40 plus 44. All right, let's take that down to where it should be. All these are going to be in feet because it's feet per second times seconds gives you feet. Here. Okay, so should I switch to the calculator or should I just do it and you'll take my word for it? Do it and take my word for it. All right, 2, 30 plus 36 plus 38 plus 4. I mean, maybe you already did this. That's 288. And then the other one, I'm going to kick out 30 and put in 44. 316. So I got 2. So what color am I using here? Okay. So this is 288 feet, and this is 316 feet. All right, so that's like my left estimate, my right estimate, my complete underestimate, and my complete overestimate. Like, so what could we say about these? Like, what's a reasonable guess, do you think, of the actual distance? I think that a reasonable guess would just be the average of these, like something right in the middle of them. So I'm actually going to do that. What happens when I average them? Well, when you average the left sum and the right sum, what ends up happening is you end up doing the trapezoids. So why does that happen? So let me try to show you. Actually, I'm going to use some iPad magic. I'm going to duplicate this and then try to show you maybe what happens. Like why is it that the sum, if I add these up and divide by 2, why is that the trapezoid? So if I add these up, let's think about what happens. So first of all, you could factor a 2 out. This is like going to be confusing math, potentially. I'm adding these, and then I'm going to divide by 2. If I add them up, there's like 2 of all of these. There's 2 of all of these. I can actually factor out a 2. So I'm going to do that. So 2 comes out. And then there's a 30. But then look, there's 2 36s. There's 2 38s. There's 2 40s. But then there's only 1 44, right? So that's when I add them together. For the trapezoids, what I want to do is I want to do 1/2. Now, if I'm doing trapezoids, look at our table. Every one of my trapezoids, remember, is going to have a base, or a height rather, a height of 2. So that's actually what this 2 is. This is actually the common height that all of our trapezoids have. And then when you're making trapezoids, so it's going to kind of go like this. I don't know, 30, 36, 38, 40, 44. Okay, so I'm going to pretend to make my trapezoids. Well, I'm really going to make them, actually. So you use this thing once, right? And you're going to make a trapezoid. And then this segment here gets used, so that green segment gets used for the first trapezoid. When you make your second trapezoid, it gets used again. Right? So now we've used this twice. And then when we make our third trapezoid, we're going to use this segment again. So we now used it twice. So we only used this once, but we used this twice, this twice. We're going to use this twice when we make our next trapezoid. But then this one, the last one, only gets used once. So if you look at this, it gets used once, twice, 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 and then once. So look at that. It's just happening when you add them together. So we get 2, 1/2, 2. Each of these was 2. This is your 30. This is 36, 38, 40, and then 44. So that's why it happens. It's 1/2, 2, and then 30, 2 times 36, 2 times 38, 2 times 40, and just 144. And then, I mean, I don't really need to do the math on that, because what I can do is I can actually add these and divide by 2. 5, do I want to do that? 98, 104, 604, 302. I'm going to say 302. Sure. I think it's 302. 302 feet. I think that that's a good estimate. It's the average of the left and the right. Turns out it's also the trapezoid, however you want to think about that. What is the maximum possible difference between your guess and the actual distance? Okay, so our guess, let's think about this. Our guess is 302. The lower estimate, the lowest it could possibly be, is 288. And the distance between these is 14, I think. Our upper, I mean, this is the way the average works, so like it shouldn't really be that surprising, is 316, and the distance between these is 14. So if we say that we think that our estimate is 302, the most we could possibly be wrong. So the most we're off by is 14 feet. Guaranteed the amount is 302 feet plus or minus 14 feet. So that's actually here where it says state your estimate along with your bound for the maximum possible error. That's got to be what it is. So we can be at most 14 feet. So I'm going to say distance equals 302 plus or minus 14 feet. That's a really useful thing to tell someone. Like if someone says, how far did you go? 302 plus or minus 14. So then somebody would be like, well, did you go 320? And you can be like, guaranteed we did not go 320 because the most we could have gone is 316. Did you go 285? Guaranteed we did not do that because the least we could have gone is 288. So 302 minus 14. Might you have gone 307? Definitely, that's in there. It's possible that we did that. So I think this is a really good kind of like thought process. Looked at a trapezoidal and or average of the left and right. They're the same thing. Didn't do anything with midpoints. It's very rare that you do things with midpoints. Not impossible. And actually on this one, you could have done midpoints. You could go 0 to 4. So the base is 4, and then the height is going to be 36 because the midpoint's 2. Find the height there. And then you go 4 to 8. Then 6 is the midpoint. You're going to find the height there at 40. So you would do 4 times 40. That would be your midpoint estimate, but that's not an upper or lower. That just is a different estimate. So good page. I'm going to call this video here, and I'll be back in the next one to do some more. So I'll see you there.